We'll start on time, I guess. And our first speaker this morning is Annika Peter. Welcome, Annika. And she'll talk about counting the dark matter halos.
All right. Thank you so much for having me here. So we've heard bits and pieces of the particle physics of dark matter this week. And so it appears the theme of today's session is astrophysical dark matter, with this being the first. Okay, so I'm going to tell you about why counting dark matter halos is what you might want to do in order to figure out what dark matter is, and one way to try to count those dark matter halos. Okay, let me set a little bit of context first. So we know, based on a plethora of cosmological measurements, that there's about 6 times more dark matter than ordinary matter in the universe. And the reason that we know this is because dark matter affects the evolution of the universe in not very subtle ways. So this is a beautiful NASA diagram of the history of the universe from the Big Bang till today. And this outer envelope here shows the expansion rate of the universe. So we have a couple of periods of accelerated expansion, so inflation and dark energy, where some field or modification to gravity dominates what we think of as the energy budget of the universe. But for much of the history of the universe, the homogeneous evolution of the universe was really governed by dark matter. Dark matter was the dominant component of the universe's energy. Okay, so dark matter is important because it governs the expansion history of the universe, the sort of how globally our universe works. But dark matter is also essential in explaining the inhomogeneous evolution of the universe. So at the time of the cosmic microwave background, matter fluctuations in the universe were of order of part in 100,000. Those little other densities, those little fluctuations grew and grew and became the system of galaxies that we see today. So the connection, sorry, wrong button. There we go. So the connection between galaxies and dark matter is illustrated in this beautiful graphic from Risa Wexler and Jeremy Tinker's review article on the galaxy dark matter connection. So if you were to run a simulation of the universe and look only at the dark matter component, you would see this web of structure on the left. Now, if you were to put your optical goggles on instead of your dark matter viewing goggles on, you would see something like this. The galaxies would be distributed like this. So this tells us that there is a close relationship between this dominant dark matter component of the universe and the visible component of the universe that we can see with our standard model observing facilities. Okay, so the connection through decades of work by many people, we now have this model that galaxies are really the tip of the iceberg in a much larger dark matter structure. So this image here is a surface density map of dark matter from simulation by Dvorkin. And the dark matter density is coded by colors. So the white spots are high density, the darker purple spots are low density. And we see that we have this overall macro structure, this self-gravitating cloud of dark matter that we call a halo. There are lots of little smaller structures in here that we're going to talk about quite a bit later. these are called subhalos. And then the main galaxy lies at the center of this vast dark matter structure. So one way to think about this is that a galaxy is like a bird's nest. So the nest itself is like the dark matter halo. And you need that dark matter halo, in order for the little chick or the galaxy to form. It's actually very difficult to form galaxies without dark matter, just like you really need a nest to deposit an egg so that it can hatch and then turn into this very hungry creature like here. Jokingly, I think of this as being open for gas accretion so it can grow into an even bigger galaxy, but I don't want to take the analogy too far. Okay, so we have this connection between galaxies and these big dark matter structures called halos. Now we could go one step further. We know, stretching this bird analogy perhaps a little farther than if you go, we know that there are different types of birds that have different sizes. So we've got a tiny hummingbird over here and an ostrich over here. This is actually, I think, a nest, big nest out of basically plywood sand, which is kind of interesting. Okay, but the other thing that you might notice, aside from the fact that the hummingbird is very small and an ostrich is very large, is that the size of the bird is correlated to the size of its nest. Okay, so the hummingbird has this teeny tiny little nest. That's a measuring tape that says that the nest is about 2 inches across. So for those of you not used to thinking in, bizarre American units, that's about this much. And then the ostrich has this very large nest. Okay, and so the same thing is actually true for galaxies. Very small galaxies, like this relatively nearby dwarf galaxy, live in a small dark matter halo, whereas a bigger galaxy, and this is a beautiful first image of the Whirlpool galaxy with JWST. The big spiral galaxy lives in a much larger dark matter halo. Okay, so the two things to remember is that galaxies live in dark matter halos. Small galaxies live in small dark matter halos. Large galaxies live in large dark matter halos. And that connection becomes really important when we want to test theories of dark matter. Okay, so our standard cosmological paradigm of dark matter is that it is cold, collisionless dark matter. So this is a simulation of the sort of dark matter halo that might host the Milky Way. And you can see that it has a lot of structure in it, a lot of these small dark matter halos that live inside of it and also live beyond it. But there's an incredible amount of structure on these small scales. Now, if you go beyond this dominant cold dark matter paradigm, things look quite different. So the main way in which these other theories, or I should say they're really classes of dark matter model. The way these classes of dark matter model differ is typically whatever you do to the Lagrangian of that theory, the cosmological effect is that you wash out these small dark matter halos. Now that may be because in the case of warm dark matter, you have free streaming in the early universe. In the case of late decaying dark matter, it's because you initially have some cold dark matter candidate, but it's unstable on cosmological scales. And so when those particles decay, you can also disrupt dark matter halos. Or in the case of these fuzzy or ultralight dark matter models, you just get a very different structure of them. The main point here is that the way most of these non-cold dark matter theories or models differ from cold dark matter on a cosmological scale is that they do not have many, if any, small dark matter halos. Okay, and so our goal when we're trying to count dark matter halos is we want to count small dark matter halos as a function of their mass and see if they match our predictions for cold dark matter or for these other dark matter models. Okay, and so one of the ways that my group and many other people beyond us have been doing this is that we're really using this galaxy halo connection to count dark matter halos. Okay, so the way this works in theory space is that you start with some model of dark matter, and then you use a simulation to tell you what the structure of dark matter is throughout the universe. You want to know what is your halo mass function. You want to know the internal mass distribution within those dark matter halos, and you want to know how those halos are clustered. Okay, and there's a recent SNOMAS white paper on this topic that I would point you to. In general, there were many very good SNOMAS white papers that, anyways, for me, I've been learning a lot about different fields, trying to catch up by reading white papers. Okay, so you now know in theory space for a given model what your dark matter halos look like. Now, the next thing that you need to understand how galaxies live and look like in those dark matter halos. And so there are various approaches. So you could run a simulation that has both your favorite dark matter in it, as well as a full hydrodynamic implementation. So you could watch galaxies and halos co-evolve self-consistently in a simulation. This ends up being very computationally expensive, which is why there are relatively few very high-resolution simulations. The other thing that you could do is that you could use scaling relations to try to relate galaxies to halos. So these could be empirical scaling relations, or they could be scaling relations that you see in some simulations. And so this is a fast way to take a cold dark matter only simulation and try to layer galaxies on top of it. And then finally, you can then take this, you have your distribution of halos, you've identified galaxies with those halos, and then you can make predictions. So typically what you want to do is you want to do population statistics. So you want to know what kind of galaxies you're going to find and how those trace dark matter halos. If you're going to work with data, then you also need to model the selection function of the survey to make sure that you know what you're seeing and understand what you're seeing as well as what you're not seeing. And the dream is to go backwards. So what I showed you before was a forward model, but really then what we want to do is we want to work backwards. We see some galaxies, and then we want to translate those galaxy counts to the dark matter structures underneath, and thus the dark matter results. Okay. Any questions so far? Are people awake? All right, awesome. So I'm going to first talk about the most famous example of us counting galaxies to count dark matter halos. And then I'm going to try to convince you that going beyond that is also very interesting. So the example that I'm going to use here is the Milky Way satellite system. Okay, let's talk about what satellite galaxies are. This is a slide I pulled from my former student Daniela's thesis defense. So we start with a galaxy. In this case, for us, it's going to be the Milky Way. We call it the host galaxy. It's surrounded by one of these large, very large dark matter halos. And when I say large, the optical radius of our galaxy is about 1/100th of the size of the dark matter halo. So really, this is definitely not to scale here. Okay. Now, this host galaxy is surrounded by a bunch of satellite galaxies. These are smaller galaxies that orbit the host. And each of those satellite galaxies has its own dark matter halo that we call a subhalo. Okay. And so the big game for the Milky Way, and when we try to put dark matter constraints based on Milky Way satellites, is that we're really trying to count the Milky Way subhalos. Okay. So there are now, depending on who you talk to, what the observational status is on follow-up observations, somewhere between 50 and 60 known satellites of the Milky Way, or if you want to be correct, satellites of the Milky Way and the Magellanic Clouds. And this is a map I pulled from a paper led by Alex Derlica-Wagner, where he showed in 2015 the current state of dwarf galaxy discovery, satellite galaxy discovery around the Milky Way. These satellites can be relatively massive, like the 4 knots dwarf galaxy, or they can have be less than 1,000 solar masses in stars like Cygnus 1. So this for real is a galaxy. This is an image from one of the GPAL up there. This is an image I basically screenshotted from DS9 based on assassin data provided by TeVPA. Okay, so this is already out of date. More galaxies have been discovered since then. Okay, so what we can do when we have this wide range of galaxies orbiting the Milky Way of different sizes is we can say, are the number of galaxies we see consistent with the theory or not? So I'm showing here a plot. This is in astronomer cringe magnitude units down here, basically bright galaxies here, faint here. You can see an approximate mapping to stellar mass up there. And this is a cumulative distribution. So the black line here represents the number of satellite galaxies we directly observe in the Milky Way. And then this gray line there shows, basically convolves, or what we see with the survey selection functions. In this case, the dark energy survey and pan-star surveys. So that gray line is our best completeness corrected luminosity function of galaxies. And then this blue line here is a dark matter plus galaxy evolution, or cold dark matter plus galaxy evolution model for the Milky Way satellite system. This is from a very nice paper by Ethan Nadler. And what we see is that the cold dark matter prediction matches our observed small galaxy distribution. And you can use that to set quite tight constraints on dark matter physics. So this is another paper by Ethan in collaboration with the Dark Energy Survey to set constraints on sterile neutrino dark matter, in this case a sheaf-fuller sterile neutrino, where we are able to use the large number of Milky Way satellites to basically exclude sterile neutrinos that have too high of a free streaming velocity in the early universe. Okay, so you can set very strong constraints on dark matter physics based on the abundance and distribution of Milky Way satellite luminosities. Interestingly, in the context of cold dark matter, this means that pretty much every subhalo of the Milky Way that fell into the Milky Way with a mass of 10 to the 8 solar masses and higher has to be occupied by a galaxy. So when we use our galaxy halo connection models to translate from this to a halo mass function, we show that every halo has to be occupied by a galaxy, at least down to 10 to the 8 solar masses. Okay. Could also check out the talk from Ariane Decker from Tuesday to learn more about this as well. Okay. Additionally, you can use the stellar kinematics, or for other galaxies, gas kinematics, to tell you something about the central density of these dark matter halos. And it turns out when you combine that information, the velocities of stars as well, you actually get even stronger constraints. So this is from a paper by my former Stacy Kim and me, where we're now looking at the cumulative distribution of galaxies now as a function of their central stellar velocity distribution. All the models we have in here have the same halo mass function, but because the stars inside, in this case for a self-interacting dark matter model, the halos have different central densities. For each dark matter cross-section, you get a different velocity function because the matter distribution in the halos differs based on how strong the dark matter self-interaction is. So you can actually set even stronger constraints with the atom velocity. Okay, so the takeaway here is that there is no missing satellites problem, but people are always worried that we've overtuned some of our galaxy halo connection solutions to the Milky Way. So let me just say that we now are in an era of trying to do this sort of galaxy halo matching for teeny galaxies, now outside of our very local environment that we call the local group, and now go out to what we call the local volume, out to about 11 megaparsecs. And the reason that we think that we can do a lot of cool stuff is because when you look at known galaxies as a function of distance and luminosity, which you can really take as a proxy for stellar mass, we find that there is enormous observational incompleteness. There should be galaxies in this space, if what we think is going on with the Milky Way is universally true in terms of tiny galaxy counts and thus tiny halo counts. We just have to find these galaxies. Okay, and so I'm not going to explain surface brightness in 2 minutes, but basically the issue is that tiny galaxies are not only very low luminosity, but their light is super spread out. So you basically get hit doubly hard to try to find little galaxies. They're low luminosity and super diffuse. And so you really need very sensitive, low surface brightness facilities or observations to detect them. So let me just say that there are a couple of different techniques people are using now to look for these for tiny galaxies outside of our local group. One is that people are just recycling data that already exists, which I call the data raccoon approach. So it turns out even in the Sloan Digital Sky Survey, people are finding more nearby dwarf galaxies, like in this paper by Oliver Milla. My group has been recycling Chris Tochanik's data to look for failed supernovae. We're repurposing the data to find very tiny dwarf galaxies that are very nearby satellites of these galaxies. So this was part of the thesis work of my students, Bianca and Chris, who both recently graduated, and my student Kirsten Casey is following up to do distances. So if you want to know about why distances in the local volume are hard, I'm happy to talk later. We've gotten a bunch of tiny galaxies. There's a very interesting recycling program that was led and developed by recent Princeton grad Scott Carlston, where he repurposed a bunch of CFHT data and found a couple hundred satellites of nearby local volume galaxies. One thing you might notice is that I'm saying satellite a lot, and that's often because when we're repurposing data, those were data taken to explore bigger galaxies. somewhere, and so by necessity, we're typically finding satellites. Also, satellites are nice because if you have a big galaxy, you know it's going to have a family of smaller dark matter children around it, or galaxy children. So that's great. My group is also working with the Dark Energy Server to look for more small galaxies. And then there are also dedicated searches. So Christine Speckens and I are involved in the SNAP survey, where we're taking DECAM and HSC to image the virial volumes of nearby Magellanic Cloud mass systems. And then there are bespoke new facilities whose goal is really to look for extremely low surface brightness structure in the universe, like the Dragonfly telephoto array. Okay, I'm only hitting a few things, mostly things that I'm most connected to, but there are a lot of people working in this field in different ways. And the reason that we're all working and excited is because a lot of what we're doing now is going to be transferable to the Rubin Observatory, the LSST on Rubin, which should expect things to really get going for that facility toward the end of 2024. But LSST will blow everything else out of the water. It's going to cover half the sky at a depth that we're now achieving by laboriously tiling the sky with DECAM and HSC. Okay. So let's summarize. So the cold dark, just the basic cold dark matter and galaxy evolution model is surprisingly robust when we are counting dark matter halos by counting galaxies. But things are right now getting real exciting. So with the Rubin Observatory, and then I didn't talk about radio detection of dwarf galaxies, but with the SKA in the future, we're going to have an amazing amount of data in the optical and radio on tiny galaxies. And so we should really be able to set very strong constraints on the nature of dark matter, or discover something very robust with the next era of optical and radio surveys. Okay, thank you.
Great.
Thanks for the great talk. So is it easy to use like anything to kind of check your galaxy and the halo like relation?
Okay. So lensing is an amazing tool. We can't use it for these exact same galaxies, but there are many different lensing efforts to test, theories of dark matter at small scale. So you should talk to, so we have a whole session on, oh man, you're gonna have to remind me, Wednesday on lensing. So Daniel Gilman and Brenda back there, he could want to wave. They worked on substructural lensing. There are other people whose names I don't remember. I just know them because we collaborate. So there's substructural lensing, which is amazing. But also, we're now going to be able to do weak lensing for sort of much lower mass galaxies than people were traditionally doing in the Sloan and HSC eras. So I've been involved in a project called Marion to measure halo masses for Magellanic Cloud type galaxies, and it's going to be even better with it. So yes, lensing is extremely important. There are many ways in which lensing is important.
Thanks.
Other questions?
I was wondering if you go back to the slide where there's the standard cosmological model with the satellite counts. There's like I don't know below that. So the missing satellites problem so quickly disappeared that I've actually lost track of where it was to begin with. Yeah, the spot. So can you describe on this plot where sort of the missing satellite problem was?
Uh-huh.
Because, yeah, my main confusion is that if the fiducial LMC prediction here is correct, and then the DS and PS1 data is correct, then it would have just been the case that before we had a deep enough survey, we just didn't have the left side of the data.
Right. Okay, so there are actually a few things going on, and I could go on for a very long time about it, but I'll try to stick to the highlights. So as we say, prior to about 2005, we only knew about galaxies over here. We didn't know of any galaxies down here. So one major revolution was that basically everything over here has been discovered in the last, less than 20 years. So the missing satellites papers were all written in about 2000, so predating the discovery of all of these. Okay. There are two other key things. One is that people have put a lot of work into understanding survey selection functions. So we can't see Segway 1 out to the virial radius of the Milky Way. In fact, Segway 1 it was only barely detectable by the Sloan Digital Sky Survey. So for every Segway 1 that we see, there are dozens of Segway 1s we expect to find in the outer part of the Milky Way's halo. The third thing is that the missing satellites problem was actually originally characterized in velocity space. And there were a lot of assumptions about mapping kinematics of stars to the mass of the dark matter halo, which turned out to just be not correct. I think Christine will talk a little bit more about how you use kinematics to match the halos, but anyways, it turns out it's more than one thing. We also understand a lot more about galaxy evolution now as well. So we can only see a dark matter halo through this technique if it actually has luminous matter in it. And so understanding how that works was also cool. So I guess those are the four things that have changed in the past 20 years.
Thank you very much. I think we'll thank our speaker and we can. Next talk is going to be delivered virtually, so the biggest one is take Joe a moment to get it set up.
You guys speaking?
Yes.
Okay, I'm going to kind of give on a little bit, but sounds like we're all set to go.
Hi, Cora, welcome.
Thank you.
Ready to hear from Cora Dvorkin. Working at Harvard University. The universe is a lab for dark matter physics. Thank you. Go ahead.
Okay, well, thank you very much for the invitation. And so today I will be talking about work with my research group on trying to understand dark matter microphysics, both at small scales using strong gravitational lensing. So this is going back to the question in the previous talk. I hope I will be able to convince you that strong gravitational lensing is a great tool for understanding dark matter at small scales. And in the remaining time, I will tell you about the new statistical approach that I have developed, I have been using with my group to analyze larger scale data sets. Okay. So, so I'm showing you here the matter power spectrum as a function of wavelength. The black line here shows the prediction of our lambda CDM standard model of cosmology. And each of the data points that you see at large scales is a measurement interpreted within the context of this model as a measurement of the power spectrum. So you can see that this figure is spanning 4 orders of magnitude in length scale and a wide variety of cosmological probe, and we can see how the lambda CDM model fits them all beautifully. On smaller scales here, however, there is a lot of structure, but it is not as well understood. And Furthermore, many dark matter scenarios that agree at large scales, maybe by construction, show differences at small scales. So observations at small scales provide fertile grounds for testing different dark matter scenarios. And as an example of the effect of different dark matter models on galactic scales, and much of what Annika was just telling you about, I'm showing you two different projected dark matter densities coming from high resolution embodied simulation. One coming from a simulation in a CDM scenario. I don't know if you see my cursor, but here on the left. And on the right, I'm showing you a simulation with some exotic dark matter microphysics that results in dark matter terms that are more susceptible to tidal streaking. And you can already see by eye that there is a lot more structure in the CDM model than there is in this exotic dark matter scenario. And this is just an example, like what Annika, the examples that Annika was showing you about classes of models to illustrate the fact that dark matter physics can lead to interesting phenomenology that is observably different from CDM and scales. And so our tool for this will be galaxy strong lensing. And so the idea is that some structure in the halos of galaxies will locally perturb lens images. So by looking at the residual between an image predicted by modeling the lens galaxy as a smooth mass and what is actually observed, we can infer the preference of subplanes. And the advantage related to other methods for detecting dark matter is that we do not need to assume a specific coupling between the sunlight and the dark matter, in contrast to what is generally done in direct detection searches or other indirect detection searches of colliders. And so in this sense, I like to say that the near model will be better. And furthermore, I will be focusing on the lowest mass halos, and by this I mean below about 10 to the 9 solar masses, which are largely devoid of stars. So detecting them in the gravitational technique is the only possibility that we have, since these halos cannot be seen directly. So with my group, we have done work in this arena following two different and complementary approaches. The first approach is what I call a direct detection approach, where we want to marginalize our individuals and halo properties to learn. The direct detection approach, here our goal is to resolve individual more massive perturbers, and from there infer their properties. And the second approach, the statistical detection approach, is where we want to marginalize our individual subhalo properties to learn about the subhalo population characteristics. And so basically in this statistical detection approach, we are exploring the stiffness of the subhalo mass function. The expectation that we have a huge population of these very low mass subhalos to try to statistically detect them as a collective perturbation. So I will start with the direct detection approach, which is the most intuitive one. And once I walk you over this approach, we will move on to the statistical one. And so the underlying principle in direct detection is that if you have some dark line views from imaging projection, there might be some visible distortion that you can try to reconstruct. And so once you have a smooth model image, assuming that there are no dark matter clumps, you can try to minimize the residual between the data and the model to ultimately reconstruct the surface mass density that gave rise to the original data set. And in this particular case, you can see that the reconstructed mass density has an over-density over here. And this was a 10 to 12 sigma plate detection of a dark matter clump line at this position in the image. So far, using this method, there have been 3 detections of subhalos in the order of 10 to the 9 solar masses from about 30 or tens of images analyzed. And what I want to emphasize here is that this is a very computationally expensive process, and it can take up to months to analyze a single system. So if you have ordered tens of images to analyze, that's okay. But in the next few years, we expect tens of thousands of these lenses to become available through the Dvorkin Observatory, Euclid, and other experiments, in addition to further follow-up by the Hubble Space Telescope, the James Webb Space Telescope, and the ELT, among others. And in fact, there are already many recently discovered by DES that are waiting for follow-ups. And this is great, since we should should expect a leap in our understanding of dark matter, but obviously it is unsustainable to take months to analyze each system. So it will become more and more crucial to use faster algorithms for analyzing the data. So what motivated us, together with my former PhD student, Annika Peter, was the following question. Can we automate a procedure like direct detection using machine learning techniques, making this process much faster? And the idea is that if we understood the sensitivity of our machine learning model well enough, we could still combine detections and non-detections to probe different dark matter scenarios. And so this work that I'm showing you over here was the first one of several in the literature that attempted to solve the problem of directly finding substructure with machine learning in the new era of TeVPA. In our first work, we used a very simple architecture, a convolutional neural network. And we then took the problem a step further in this work over here with my former postdoc Brian and Ossie, and tried to cut the middleman entirely. We tried to convert the entire detection pipeline into an image segmentation task. Image segmentation involves taking an image and trying to understand what the individual components that make up this image are. And we use for this a network called units. Units are basically networks that are well known for their success in image segmentation in biomedical research. And we saw here that the network struggled to find the lower mass subhalos, but it did fairly well for subhalos above around 10 to the 9 solar masses, which are masses comparable to the ones using standard. Moreover, we show that the network can actually find not just one subhalo at a time, as it was trained for, but in fact it can find many at a time. And here on the left, I'm showing you one such example where you can see that it can find the more massive subhalos, and of course we fail to find the lowest. And so now since we can find many in each image, we can think about combining many of these images to measure the shape of the subhalo mass function, which gives us insight onto the nature of dark matter. And we can see here on the right how combining more and more images, of course, reduces the error. And it is interesting to know that if you combine, say, 1,000 images, you can get down to 10% error bars in the logarithmic slope of the subhalo mass function. So this is quite exciting. Okay, so let me switch gears now to talk about the statistical approach, where we marginalize over the individual subhalo properties now to obtain subhalo population characteristics. So I will start by considering the limit in which all of the perturbers are substructured that live in the lens, and then, so they are subhalos, and then I will move on to the much more general case of the full 3D distribution of perturbers. So in a paper with Annika Peter and Francis Yanes in Brazil, a former postdoc at Harvard, who is now a professor at the University of New Mexico, we developed a general formalism to study the endpoint function of the convergence field, or the surface mass density. And we started from the power spectrum. Basically, if we have a lot of substructure, the perturbations would look very close to Dvorkin, the central limit theorem will begin, and most of the information should be in the power spectrum. So what we did here is that we modeled the convergence field as a substructure component superimposed on a smoothly varying density profile of the host. And the convergence field of the substructure depends on the position, the mass, and the intrinsic properties of the subhalo. So here we propose to change of language, moving away from talking about subhalos, and instead we propose to talk about the correlation function of the projected density field. And the advantage of this is that we don't need to define what we mean or don't mean by a subhalo, as it's generally done in the literature, many times with different definitions. So we started from first principle. We described the power spectrum in terms of what we call a one subhalo term, analogous to the one halo term, which arises from ensemble averaging over the spatial distribution of single subhalos, and a two subhalo term, again in analogy to the two halo term, which arises from averaging over pairs of distinct subhalos. And so note that here we are taking integrals over probability distribution functions of the mass, the intrinsic properties, and the spatial distribution within the course. So here's our power spectrum. I'm showing here that one subscalar term for the remaining of the talk. I will be ignoring the two subscalar term. You can ask me about it at the end if you're interested. So we can see that the power spectrum is mainly described by three quantities. At low K, or large scales, we have a plateau, a constant amplitude. Here we're probing scales that are much larger than any subscalar in the system. And so at these very large scales, all the subscalars are essentially point masses, and the Fourier transform of that is white noise. As we move on to smaller scales to the right, we have a turnover scale given by tidal interactions of the largest subscalars in the lens balance. And if we keep moving to even smaller scale, we reach an asymptotic regime. So the power spectrum asymptotes to a power. And the slope here of this of the power spectrum reflects the properties of the inner density profile of subscales, which will be different for different dark matter scenarios. In particular, for an LFW profile, which we describe as the scenario, it will go as 1 repeat to the 4. If we have a non-trivial dark matter scenario, the density profile will change. Here, I think as an example, a self-interacting dark matter scenario with a 4 profile. You can see here in the given line. And we can see now that at small scales, the slope goes of 1 over Q to the A. So here we have a promising theoretical prediction to distinguish between different dark matter scenarios. However, notice that these are very small scales. And here I'm talking to distinguish between these two scenarios, and we are talking about scales that are smaller than about 50 inverse kiloparsec. And so these are scales that we will probably not be able to reach in the near future. But we saw later that by adding redshift information, we can use the information at larger scales, which are accessible by near future experiments, to distinguish between different dark matter. And this is what I'm going to show you next. These are results from high resolution and body simulations that we analyzed. On the left over here, I'm showing the evolution as a function of redshift of the power spectrum in a CDM scenario. And we can see that the evolution is quite intuitive. As we evolve in time, we go up in this figure. The amplitude is increasing, and this is because we are doing more and more substructure as time goes on. And on the right here, I'm showing an exotic dark matter scenario, which includes a low mass cutoff in the initial power spectrum and dark matter of interaction, which made the subscalars less concentrated and so more likely to be tidally disrupted. And you can see this reflected in the fact that the amplitude got stalled now between redshift of 0.5 and 0. The increase in accretion in substructure is being compensated by the fact that a lot of substructure is being destroyed. And we can see it's as a net transfer of power from larger to smaller scales over here. And so this is reflected in the change in the power spectrum slope compared to CDM for wave numbers greater than about 2 inverse kiloparsec. So note that the scales now should be less sensitive to variance, since large variant structures such as giant molecular clouds or globular clusters are expected to dominate at smaller scales than wave numbers. So they are expected to dominate at wave numbers greater than about 10 inverse kiloparsec. And we are currently working on quantifying this. And these scales are accessible by near future experiments. So we just saw the convergence power spectrum of subscalars within lens galaxies is a promising observable to study diagram. However, we expect a relevant volume to contain line of sight scalars that are not necessarily associated with the main lens. And in this work that I'm showing here, led by two of my graduate students, Chance and Wu and Arthur Fan, we studied how the relative contribution to the power spectrum of line of sight scalars and subscalars depends on the source and lens redshift, as well as the assumed scalar and subscalar. And here I overlaid points that correspond to the bells and slats families of galaxy lensing. And in particular, these are sets that have been used to play constraints on Dark. And we can see that for both sets, for a fraction substructure that we think is more realistic, basically from upper bounds in the literature, and this corresponds to F sub of about 0.4%, these systems are likely dominated by the halos along the line of sight as opposed to subhalos as they were assumed in the previous slides. And the fact that for typical lensing configuration, the line of sight halos dominate the signal, we think should be good news. The subhalo assumption is very hard to pin down, while in comparison, halos along the line of sight leave relatively colored lines. So in terms of current data, we are reanalyzing systems that were previously claimed as subhalos in the literature. Basically, we use the fact that the deflection angles caused by the interloper form a vector field with a non-vanishing curve, which cannot be recreated by a single thin lensing plane. And in particular, this system that I'm showing here was claimed to be a subhalo in the JVAS lens in the Nature paper about 10 years ago. And we find, redoing the analysis with decisive evidence, that it is likely a line of sight halo. We also found that it is more massive than the previously claimed by about an order of magnitude. And so this is, to our knowledge, the first that shown to be a line of sight halo with a gravitational lensing method. Now, measuring the total mass of the perturbers from strong lensing data is challenging. And this is important because over-estimating the mass can lead to incorrect inferences about the nature of dark matter. And so in a recent paper with my student Chantal Wu, we showed that instead of using the halo mass function, we can use an effective matter density slope measured from lensing data to distinguish between different dark matter scenarios. And I'm showing here the results coming from simulations. And so we found that our measurement of the effective density slope of the JVAS perturber that I just told you about is steeper than what is expected in the CDM scenario by about 2 sigma. However, of course, steeper perturbers have a stronger lensing signal, which makes them more likely to be detected. So what we pointed out is that we need more measurements of this time to draw robust conclusions about the nature of dark matter. And we are currently working on with another of my students, Jen Marzan, on trying to harness population level statistics of the effective matter density slope using machine learning techniques. Okay, let me see how I'm doing in time. I have 10 minutes left. So let me tell you very quickly about our work on larger scales. So basically, what I showed you up to now is how we can use gravitational lenses to probe dark matter at kiloparsec scales, which is a regime that so far has remained much less tested in comparison to the larger scale. But we can also use observables at different scales and relevant times as a powerful lever to probe new physics. And so the last few years have casted critical lens and lambda CDM as possible cracks in the model have started to surface. The most notorious tensions of cosmological parameters inferred from different data sets correspond to the expansion rate of the universe, H0, and the amplitude of matter fluctuation, ranging from 3 to 5 sigma, depending on the observable periods. And a variety of new physical models, almost at a daily basis, have been proposed to solve each of these tensions, ranging from non-standard dark matter models to new light particles and forces. But whether or not these tensions point to new physics remain an open question. And so in the upcoming years, we expect a deluge of data from cosmological surveys mapping even more precisely the distribution of matter in the universe. So it is timely to work towards extracting the information buried in the data as precisely and accurately as possible. And to this end, we investigated the prospects of using a novel approach to extract information from non-Gaussian fields, and this is what I will tell you about in the remaining little time that I have left. So, when analyzing cosmological data, the first thing that comes to mind is the power spectrum. But as you all know, if the field is non-Gaussian, the power spectrum doesn't contain all the information. And this is the case of for the larger structure of the universe. The traditional way to go beyond the tower spectrum is by computing higher order statistics. One disadvantage of endpoint functions, a topic that I have worked a lot in the past, is that it fails, these endpoint functions fail at capturing all of the information when the field is highly non-consistent. And this was shown in a nice paper by Cora in 2011. Another disadvantage is that it rapidly becomes computationally infeasible once we go to higher and higher point function. On the other hand, in recent years, we saw an increased use of machine learning techniques, for example, convolutional neural networks, to extract information at the field level. However, its application to actual cosmological surveys is still an open question because of many issues, mainly the lack of transparency and interpretability. So a nice combination of these two approaches was done by a mathematician 10 years ago through the wavelet scattering transfer in the context of computer vision and signal processing. So the wavelet scattering transfer, or WST, is a process to generate summary statistics that borrows some of the ideas from convolutional neural networks. Okay, so now let's talk very quickly about some details about the definition of the scattering transfer. Basically, from the input field, we first pick a scale by convolving it with a curve, or a wavelet with scale J and orientation F. We then take the modulus of the convolved field, and the purpose of this is to get the local strength of fluctuation. And in fact, the power spectrum can be defined in a similar way in Fourier space. We can define the power spectrum as the convolution and the nonlinearity, and we can see the similarity with a neural network already. The power spectrum is basically a one-layer convolutional neural network. So one convolves the field in a Fourier loop and get the complex value field, and so one can define the power spectrum as taking the modulus at each pixel, taking the square of it, and then doing the spatial leverage. But the power spectrum cannot probe the interaction between scales. It is a single scale analysis. And so to go further, we can replace the kernel with a local kernel over here and drop the square defined in the power spectrum. So we can then go easily to the next layer. And if we didn't use a local kernel, the next layer would be infinite. And since we drop the square, we're always proportional to the field intensity itself. And finally, to construct translation and invariant statistics, we take the spatial leverage in a convolutional neural network. This goes under the name of local. Okay, so here we have the zero first and the second order scattering coefficients. And at each layer, we can have a variety of scales. And this leads to a structure of the scattering transform that resembles the structure of a convolutional neural network, but with the difference that the scattering transform uses a preset library of kernels, which are the wavelets. And these kernels are not learned by the data. So this is why the scattering transforms are more interpretable. It can be, basically the wavelet scattering transform can be interpreted as an endpoint correlation function being by wavelets. At zero order, this is just the mean value of the field. At first order, we encode the information about the strength of the clustering at downloadable scale and orientation, which resembles to some degree the familiar power spectrum. At second order, we encode information about the cluster structures, which resembles the 4-point function, and so on. And in fact, we saw in a paper with Jordi Falogianis last year that this WST coefficient applied to 3D simulated matter density field can perform much better with the power spectrum or the matter power spectrum statistics that we see in the long press a few years ago. Okay, just very quickly, and I will skip a lot of details here in the interest of time. We use Abacus HLD simulations from our colleagues at the CFA with a grid cell of 10 megaparsec over H. We have to cut the simulations into a CMAS geometry, which is the data set that we use. We use WST coefficient up to second order, and it's a benchmark. We compare our results with the multiple and quadruple of the power spectrum up to K-max of 0.25, 8 inverse megaparsec, which is roughly the smallest scale we are probing with the wavelet. For our likelihood analysis, we use the Gaussian likelihood, and we vary 4 cosmological parameters and 7 HLD parameters. So just before I show you my final slide with our results, I want to mention some limitations of our analysis. First, the amount of simulation that we use so far have been fixed under the size of the horizon, fixed to the planned value, okay, which in principle we would like to vary. Second, and more importantly, to lack of enough simulation covering the field parameter space, we use the Taylor expansion using linear derivatives around the fiducial model. And we are working on overcoming this caveat by building an emulator. Finally, the systematic weights that we use and the fiber evolution weights have been optimized for the 2-point functions. And so they should be re-optimized for a field level. And this is generally true for analysis that you may see using these type of data sets for the bispectrum or the trispectrum. They're all using weights that have been optimized for the 2-point function, so they should be re-optimized. And we are planning to participate in a mock challenge to test our pipeline and apply it to upcoming DESI data. Okay, so here's my final slide. I will skip a lot of details here. Ask me about it if you're interested, but these are our results. So basically, I'm showing here a comparison between the constraints from the power spectrum in red and the ones from our three-dimensional weighted analysis in blue. The mean values are broadly consistent with each other within one sigma of the power spectrum. And we can also see, obviously, that the WFT errors are much tighter. And we check that this is mainly coming from the second order. So this is quite exciting. And an interesting thing to note is that our sigma A constraint is in tension with the one obtained by the clock. Okay, so I reached my 29 minutes. So let me leave you with my final slide. And basically by saying that we expected wealth of new complementary data to be measured soon. And this will offer many opportunities to build and exploit new powerful techniques. So stay tuned.
Thank you. So, do we have any questions? Yes.
Here, so perhaps you to repeat the question.
Yeah, I'll repeat it if necessary, but we're still watching up to the person who's going to ask the question.
Thank you. I have perhaps a very technical question. This wavelength scattering just transformation, the thing that we have been using. How do you select the scale of the wavelength of the wavelength? Or do you use the normal wavelength transform here at different scales?
Sorry, I didn't understand.
Okay, so with your new wavelength technique that you're using, how do you select the wavelength that you use?
The wavelength that I use.
Yeah.
So this wavelength scattering, let me show you here. 1 second. Yeah. So here is the wavelength, the 3D wavelengths that we are using. Okay. So the choice that I have is of this sigma. Yes. So basically the size of the patch. So the size of the envelope of the Gaussian that is being convolved, that is convolving the spherical harmonics, and the size of that, the variance of the Gaussian has been chosen to optimize parameter constraints from simulated data. Okay, we chose it to be 0.8 in this analysis based on the code simulation. And what is interesting to note is that this sigma of 0.8 and this Q, which is the value at which we elevate the power of the modulus of the scattering transform are less than 1. Q less than 1 emphasizes low density regions. But basically, what we are doing here is we are choosing a sigma to optimize our parameter constraint from simulations, and particularly we optimize them for neutrino mass constraint. And we are choosing 5 scales, okay? And the 5 scales go from the largest size, from the size of the box to the minimum scale row.
And how sensitive is the result to your specific choice of these parameters? If by any chance the simulations are wrong.
How sensitive is your choice, is the results to your choice of this parameter then?
Our results are definitely going to be, so we optimize our results for this sigma parameter. Results will change, presumably we'll get worse with different sigmas. We should re-optimize it for the whole simulation. The dependence of our parameter constraints on the scales involved is something that we are actually working on. We are trying to understand how much information is coming from larger scales and how much information is coming from smaller scales. This is a very common topic in the field since, we expect a lot of new experiments measuring the smaller scales.
Okay, thank you. Do we have any other questions? If not, then I guess we go to coffee break and reconvene at 10:30.